Imagine you have two different aldehydes sitting in a flask. One is acetaldehyde, a small, flexible molecule with 3 reachable hydrogen atoms. The other is benzaldehyde, a bulky aromatic ring that seems, at first glance, much more stable. If we add a splash of sodium hydroxide, a chaotic dance begins. But here's the puzzle. Why do these two molecules, which could ignore each other or react with themselves, choose to come together to form one specific, beautiful product called cinnamaldehyde?
Welcome to the Claisen-Schmidt reaction, a classic example of chemical choreography. To understand what's happening, let's look at our first player, acetaldehyde. Notice these 3 hydrogens attached to the carbon next to the carbonyl group. We call these alpha hydrogens, and they are the secret to this entire reaction. Because they are sitting right next to that oxygen double bond, they are surprisingly acidic. Now, watch what happens when the hydroxide ion enters the frame. The hydroxide doesn't attack the carbon atom. Instead, it reaches out and snatches one of those alpha hydrogens. As the hydrogen leaves, it leaves its electrons behind, creating a negatively charged species called an enolate ion. This enolate is our nucleophile. It's hunting for a positive charge to latch onto. But here is where it gets interesting. Let's look at our second player, benzaldehyde. If you look closely at the carbon next to its carbonyl group, you'll see it has no alpha hydrogens at all. It's a dead end for the hydroxide. Benzaldehyde can't become a nucleophile. It can only sit there and wait to be attacked. This creates a perfect division of labor. Acetaldehyde provides the spark by forming the enolate, and benzaldehyde provides the target. Let's visualize the collision. The negative carbon of our acetaldehyde enolate swings around and strikes the carbonyl carbon of the benzaldehyde. In an instant, a new carbon-carbon bond is forged. Picture the two molecules now fused together, forming an intermediate called an aldol. But the reaction isn't finished yet. This intermediate is still a bit crowded and unstable. In the presence of the base and a little bit of heat, something called an elimination happens. A molecule of water is kicked out. 1 hydrogen from the original acetaldehyde side and the oxygen group from the benzaldehyde side. Look at the resulting structure. This is cinnamaldehyde, the very molecule that gives cinnamon its characteristic smell. Notice the pattern of the bonds. A double bond, then a single bond, then another double bond. This is what chemists call a conjugated system. The electrons are no longer stuck in one place. They are delocalized, spread out across the chain. This makes the final product incredibly stable, and it's actually the driving force that pulls the entire reaction forward. The beauty of the Claisen-Schmidt reaction isn't just in the new bond it creates. It's an elegant lesson in molecular roles. By choosing one partner that can react and one partner that can only watch, we find a way to build complexity out of chaos, turning 2 simple liquids into the aromatic heat of cinnamon. Next time you smell that spice, think of the enolate's hunt and the perfect stability of that final conjugated chain. Chemistry, it turns out, is the art of knowing exactly when to let go of a hydrogen.